Good afternoon, everybody, and thank you to the Programme Committee for inviting me to speak at the workshop today. My name is John McDonald. I'm a professor at the Department of Computer Science at Maynooth University, and the work I'm going to be talking about today is led by my PhD student, Louis Gallagher, whose PhD thesis is focused on the development of a collaborative, dense, simultaneous localization and mapping system. So, as I'm sure most of the participants at the workshop will know, simultaneous localization and mapping is probably the most widely studied and researched problem in robot perception over the last 30 to 40 years. The problem can be stated as that of trying to map an environment from a moving platform or sensor, while simultaneously estimating the motion of the sensor relative to that platform. So over the years, there's been many different, epochs of SLAM research, starting with sonar and radar, moving into sensors such as visual sensors. And then more recently, we've seen a lot of work in the development of dense SLAM systems that use direct methods, perhaps starting with the work of Steve Lovegrove and Richard Newcomb at Imperial College on live dense reconstruction methods and on the ConnectFusion mapping system. So multi-robot or cooperative mapping and localization is the same problem, essentially, where instead you have to create a single global map of an environment, whereas in this instance, you're doing it from multiple moving sensors, each of which is moving independently through the environment. At the same time, you're trying to estimate the motion of each of those sensors relative to that single global map. So in our work, we focus on the development of collaborative dense SLAM. So the objective here is that we wish to reconstruct a single dense model of the geometry of the environment. So by dense, we mean that we wish to use all the pixels in the image sensor as they come in at frame rate to build a very high fidelity, highly accurate model of the environment that can be shared between multiple robotic platforms, or even between, for example, a augmented reality headset that a user may be wearing in order to interact intelligently or in a perceptual fashion with a collaborative robotic system. So the focus of our work is on having a single model of the environment. So many systems, and we'll talk about one in a moment, take an approach where each mapping session or each sensor develops their own map in their own local frame of reference. And then as loop closures are found between the different submaps, a transformation is computed between an underlying pose graph in each camera's relative coordinate system, which allows the alignment of the two maps. However, subsequent to the alignment, often those maps may not be fused, which means that the data in those maps can't be immediately shared in real time between the two systems. And in fact, also what happens is as the maps traverse through the same space, they effectively end up mapping that same space in duplication. So in contrast to that, what we try to do is to have a system that builds a single map. And as the cameras obviously are started, they're in their own frame of references and don't know the inter-camera transformations, so they build their own submaps. As the system proceeds, we try to find loop closures between the independent mapping sessions to bring them into alignment. As soon as they're brought into alignment, we share the map data between the two sensors so that we minimize the duplication in the map. So this has a number of benefits. One is that it means that the scale, the storage complexity of the system is related to the scale of the environment that we're trying to map, as opposed to the number of cameras in the map. But also the fact that we can directly share information between the different platforms enables not just multi-robot mapping at, say, a large scale, which is often the focus with these pose graph methods, but we can also support it at a much smaller spatial scale, which as a consequence can facilitate multi-robot and human-robot interaction and collaboration, and essentially a shared sensing between the two platforms, allowing an increased situational awareness above and beyond what would be possible from the single robot with its single set of sensors. So although the multi-robot SLAM problem is somewhat of a niche problem within the overall SLAM landscape, it still has been studied quite a lot, and there has been a lot of techniques and research published over the years dating right back to the early days of SLAM. So an excellent and very comprehensive review of the state of the art and a historic perspective on the problem is provided by Saidi et al. In their Journal of Field Robotics paper in 2016. Now, in reviewing this paper and the various methods, what's very obvious is the lack of research that has gone on to date in applying multi-robot SLAM methods to dense perception systems and dense visual mapping systems. One exception to this is the work of Goldatz et al. From 5AI and Oxford University, where they developed a collaborative large-scale dense 3D system, which they published in 2018. So this system used the Infinitam visual SLAM system underneath and essentially allowed multiple independent dense maps to be computed in real time in parallel from multiple handheld cameras as they move through an environment. The underlying map representation is a pose graph based representation where the pose graphs in each submap represent the motion of the camera sensor within that submap. As mapping proceeds, visual loop closures are detected between independent submaps, and when they are detected, those submaps are brought into alignment and mapping continues. Now, what's different to their system from ours, as I've mentioned earlier, is that each of those submaps is still maintained independently within the overall mapping system. It is possible for all of those maps to be fused into a single integrated model of the environment through a fusion step. However, that fusion step is performed at the end of the mapping process. In contrast with our system, we try and perform that fusion step as early as possible to allow exploitation and leveraging of the map data and sensor data between the platforms in real time. So our approach at a high level consists of a number of steps. To start, we use an existing state-of-the-art visual dense mapping system known as ElasticFusion, which was developed by an ex-PhD student of my group, Tom Whelan, but was developed whilst he was a postdoctoral researcher after his PhD under the supervision of Professor Andrew Davison at Imperial College. So our system uses ElasticFusion as a foundation where each of the individual cameras is processed by ElasticFusion to build a local independent submap. We also use the Fern-based visual loop closure detection system provided by ElasticFusion to detect not just loop closures within the individual submaps, but also between the submaps. When the Fern-based visual loop closure detection system finds a loop closure or detects a loop closure between independent submaps, those maps are brought into alignment and merged together using the loop closure constraints that are computed. At that point forward, all the sensor data from each of the cameras in that merged submap feed into a single integrated or unified representation of the environment. So in order to understand our collaborative dense SLAM system, it's important to first review the underlying ElasticFusion system which we build on top of. So the ElasticFusion system was published by Tom Whelan in 2015 and then by a follow-up paper in IJRR in 2016. So it's a dense visual SLAM system that uses a circle-based representation as the underlying map representation. It divides that map into two regions, an active region and an inactive region. It uses RGBD odometry, which combines both the photometric and geometric information to provide an efficient and robust mechanism for tracking the current camera pose against the active region of the map. In order to connect or reconnect the active region and with inactive regions and reinitialize or reactivate inactive regions, it uses a deformation-based loop closure system where global loops are detected using a Fern-based place recognition system, and local loops between local or nearby regions of the inactive map are reconnected to the active area using a combination of, again, geometric and photometric information. A key innovation in ElasticFusion is that there is no pose graph. Instead, the cameras are tracked directly against the map and their poses are updated directly against the map. So as mentioned on the previous slide, ElasticFusion uses a circle-based model of the environment, which consists of a linked list of circles where each circle corresponds to a disk or a surface patch that characterizes the geometry and appearance of that point in the environment. So here on the right, you can see a reconstruction from one of the data sets that I will show later in the talk. And on the lower right, you can see a zoomed in portion where the circles are visually apparent. So each circle is characterized by a number of different parameters, which are shown on the left. First of all, it's characterized by its three-dimensional position in the environment. Secondly, it's characterized by its orientation through a surface normal. Next, a current estimate of the color of the environment patch at that point is stored. Next, we have a weight that's used in the fusion process and measures the confidence in the current estimate. Next, we have a radius which describes the extent of the circle in the environment. And then finally, we have two timestamps. So the first timestamp is the initialization timestamp, which is the point in time that particular point in the environment was first measured. The second timestamp, on the other hand, is the last point in time at which the surface was updated through the fusion process. So these timestamps allow ElasticFusion to separate the map, as I mentioned in the introduction, into two regions. The first is what's known as the active map or active region, and the second is what's known as the inactive region. So for a single camera mapping system, you can imagine it intuitively in this kind of form, where you have some environment that the system is mapping, and at any point in time some subset of the circles close to the camera or that have been seen by the camera in the not too distant past are all maintained in the active area, and that active area is used to predict what the camera should see at any point in time, and then the RGB odometry uses that prediction to align the current live input image of color and geometry with the predicted model and to estimate the camera pose. The inactive area of the map are regions that have fallen out of the local context of the camera and are stored for later reactivation and can also be used for fusion. So I suppose it's important to note that at any point in time when the camera tracking proceeds and the pose of the camera is estimated, the live information coming from the camera can be used to fuse into both the active or inactive area of the map. So for collaborative ElasticFusion, the first step that we performed was to extend this representation to allow multiple cameras, where each camera initially operates in its own independent submap. So here we have multiple maps that are started at the beginning, each processed through an independent ElasticFusion pipeline. At the start, we have n cameras that are mapping throughout the system, and we will have n maps, but later on that number of maps can drop. So at any point in time, we say that there are n cameras in the system and m maps. So any camera will be associated with a single map, but any map can be associated with multiple cameras. So in order to deal with the active versus inactive architecture used by ElasticFusion, we extend the circle-based representation where we use the original position, normal, color, and initialization timestamp, but here instead of having a single update timestamp, instead we have a vector of update timestamps. So here you can think of this vector as consisting of the timestamp at which each of the cameras last saw that particular circle or last updated that particular circle. The reason that we extend the timestamp vector is to allow us to maintain an active area for each camera independently. So this is very important because in order for local loop closures to be, or even global loop closures to be able to occur between two cameras operating, or I should say the active areas or the live areas of two independent cameras to occur, we need to be able to separate out which circles are seen by which camera and therefore be able to apply a loop closure and a deformation graph between active areas of the map. The architecture that we use in our system consists of a centralized mapping server, and that centralized mapping server takes the input data streams from each of the cameras independently and then fuses them into each of their maps, detecting loop closures and then combining the submaps into integrated or unified maps as loop closures are detected. So here to model this, we define what's called a reference frame, where each reference frame encapsulates a single map and all of the cameras that are tracking against that particular map at that particular time. So all of these reference frames are computed and managed centrally, which is a bottleneck in the current system, whereby we have this star topology feeding into a single mapping server. So each of these data streams is in the actual implementation is streamed over something called an LCM stream. So LCM stands for Lightweight Communications and Marshalling, which is a system similar to that used in ROS in the ROS topic publish and subscribe mechanism, where this system was developed by MIT during their participation in the DARPA Urban Grand Challenge to allow multiple sensors to communicate very efficiently, or multiple processes, I should say, to communicate very efficiently using a lightweight communication, distributed communication mechanism. So LCM provides two components. I suppose the first is that it provides a data marshalling component to allow interchange between data between the various nodes in the system, and it provides a communication system, which is a publish and subscribe mechanism. So in our system, all of the cameras operate asynchronously, so there's no global clock between all of the cameras. So each frame of reference, in order to detect loop closures, maintains its own Fern database to detect loop closures within its map, but then as new frames come in to each reference frame, those frames are also queried against the Fern database of the other submaps in the system. So this permits the separation between inter and intra-reference frame loop closure, where the intra-reference frame loop closure is handled by the deformation graph within, I should say, the submap for that particular camera, whereas an interframe loop closure requires an alignment between the maps and then a fusion of the maps, and then finally an application of the deformation graph to bring the camera that is currently tracking and the loop closure pose into alignment. So in this slide, we briefly review the various transformations that are involved in the loop closure mechanism and how they're applied to the two maps when a loop closure occurs. So here what you can see is a camera CJ that's tracking relative to a frame of reference RJ, which gets a loop closure between its current image and a previous camera CF that's tracked relative to the frame RI. So when that loop closure occurs, the loop closure mechanism is applied or is invoked, at which point it computes a transformation between the loop closure frame CF to the loop closure frame CJ, but in the frame of reference of the loop closure frame CF. This gives you a transformation from CF to CJ prime. We then take the transformation from the origin of RI to CF and compound that with the delta to give us a frame of reference for CJ prime in the frame of reference RI. We then take the frame of reference of CJ in the original frame RJ, and we invert that and compound it with the frame of reference of CJ prime in RI. And compounding those together then gives us the transformation between CJ and CJ prime, which can be applied to the map CJ, or MJ I should say, to bring it into the frame of reference of RI and thereby fuse both maps together. The first set of results that I want to show are the results where we evaluated the system on two well-known ground truth benchmarking datasets. The first is a dataset which was created between my own lab at Maynooth and Andrew Davison's lab at Imperial College London, between Tom Whelan when he was doing his PhD and Ankur Handa while he was a postdoc at Imperial College. And that's the ICL-NUIM dataset. So that dataset, a sample of it is shown here in the top right, where the advantage of that dataset is that it provides both ground truth poses for the cameras as they move through the environment, this virtual simulated environment, but also because it's a virtual environment, we have a ground truth surface. The second dataset that I'll show is the TUM RGBD dataset, which is a real-world dataset taken by RGD cameras where a high-speed ground truth pose tracking system similar to the Vicon type system is used to provide highly accurate pose measurements for each frame of the camera sequences as they proceed. So this sequence here shows a 3-camera sequence of computed using 3 separate sessions of the ICL-NUIM dataset. So if I play it forward, what you'll see is initially we have 3 cameras in their own independent reference frames, and on the right you will see the RGB information captured by each camera. So because of the way these trajectories are captured or have been, I should say, generated by the ICL-NUIM dataset, the 2 cameras on the bottom actually share a very similar pose and will generate a loop closure almost instantaneously at the beginning of the sequence. However, the 3rd camera doesn't generate a loop closure until much later in the sequence, and therefore you will see the loop closure later on, and you will initially see that tracking in its own separate map. So if I play this forward, you see the loop closure immediately occurs between the bottom two cameras, and then we play it forward initially in real time, but then we switch to 4x speed just to for the sake of time. And here you can see two cameras tracking independently. So this is the view from one camera, and then if I play forward further, we switch to the other camera, I believe. So here's the other camera here. Here's the third camera up here, and each of them are maintaining a separate model of the environment. At this point, we've paused the mapping, and you can see that we've just received a loop closure between the third camera and the first two cameras, which has brought all of the cameras into a single unified model of the environment. So if I play that forward even further, what you'll see is that at this point, we can see the model itself, and we can see the scale of the model and the alignment between the various different submaps. Here what you can see is the surface colored based on which camera caused that surface to be generated. So primary colors are circles where the fused measurements are from one camera, and we have secondary colors where more than one camera has the information from more than one camera has been combined to estimate that particular circle. So if I play it forward further, what you'll see now is each camera is moving independently. And you see, for example, these secondary colors where one camera is adding information to a region of the map that was originally estimated by one of the other cameras, and vice versa. So we can take these results and evaluate two things. One is the surface reconstruction accuracy, and the second is what's known as the absolute trajectory error, which looks at the error in the poses of the cameras relative to the ground truth. So here what we see is that the surface reconstruction accuracy is at the order of centimeter or sub-centimeter accuracy, which is on a par with the original ElasticFusion algorithm. The one exception to that is KT3, which is basically a very difficult sequence because at a particular point it stops whilst looking at a planar wall which has no texture, which causes the ElasticFusion algorithm itself to have difficulty in maintaining its camera track. So this is the single session results where we essentially apply the vanilla ElasticFusion algorithm with a single set of parameters where we haven't really tuned the parameters on a per sequence basis. And you can see here that we're getting centimeter accuracy or close to centimeter accuracy on the poses and sub-centimeter accuracy on the surface reconstruction accuracy. Here we see combinations where we've run KT0 with KT1, KT0 with KT2, and KT1 with KT2. So each combination of KT0 up to KT2, where we see that this collaborative mapping maintains a similar level of accuracy and a similar level of accuracy on the camera poses. And then finally, we show the three sequences combined together, where again, we maintain the accuracy in both the surface reconstruction and in the camera poses. So in this sequence, we show a sequence that we've taken from the RGBD, the TUM RGBD benchmark system, where we've taken that sequence and split it into two subsequences and treated each as an independent camera input. Initially, each starts on a different side of the bench here, starts tracking, building up its model of its particular or associated side of the bench. At this point, we get an intermap loop closure between the two cameras, where we can see the combination or the alignment between the two circle-based models. And here we can again see the coloring, where the green is for one of the cameras and the blue is for the other camera. And we get we will see secondary colors when one camera updates circles which were originally computed by the other camera in the system. So because the TUM dataset doesn't provide ground truth surfaces, it only allows the evaluation of the system based on the absolute trajectory error, where again we're showing here that we are achieving centimeter level accuracy on the trajectory error across various combinations of the sequence. So here we have a 2 and 3 camera sequence that we've applied using the TUM RGBD dataset. And here what we show is just the timings that occur. So there is an overhead that's incurred due to the star topology nature of our architecture, because each camera is being processed centrally by the single GPU. So on the left, you see the timings due to the 2 camera sequence, where we see that each pair of frames that comes in takes approximately 40 milliseconds, or we get about 22 frames per second processing rate. When we increase that to 3 cameras, that time increases consequentially, and the frame rate drops to about 13 frames per second. So both of these data sets, as I've mentioned, are indoor data sets. So based on the fact that we have had an interest on applying our system to outdoor data sets, we're now in the process of just beginning to think about how we might apply this in a autonomous vehicle type scenario. So to start this research, we've taken something known as the Urban Canyon dataset, which was developed by David Scaramuza's group at ETH Zurich, to evaluate different types of cameras in vehicle type scenarios for visual odometry and visual SLAM. So the Urban Canyon dataset consists of a scene city model, which is a model that generates procedural, or uses procedural based models to generate city type environments. And they've taken this scene city model to generate a model of a city, which they then take into or input into Blender to generate both RGB and depth maps of a camera moving through that environment. So you can see the environment here on the right, and it's a bit difficult to see, but there's a kind of a yellow or orange trajectory over the path that the camera tracks or moves through the environment. So they also provide ground truth models and poses. However, we haven't used those yet to evaluate the accuracy, and that's part of our ongoing work. So what we've done is we've taken this trajectory and broke it up into multiple trajectories where we have meeting points at intersections, etc. And then we're using this to at least explore the concept or the idea of applying this multi-camera dense collaborative SLAM system in urban settings for collaborative SLAM and collaborative visual mapping. So we have one result here to show at today's workshop, which is applying our dense SLAM system to this model. So here you see the 2 cameras starting in their independent frames of reference. So we have a camera on what we call the side street, and then a camera on the main street. This shows just the camera data, but this shows both the depth and camera data of the other camera on the bottom panel here. So similar to the previous sequences, you can see the mapping that occurs. So the depth maps obviously incorporate depth out to quite a large distance. And here what we see is that each camera tracks and reconstructs its environment independently. So as the mapping proceeds, we have one camera which is coming in one direction and the other camera coming in the other direction. At some point here, we get a loop closure between the 2 cameras, which allows us to align and combine the 2 maps into a single model of the environment. So the mapping is paused at this point just for visualization purposes, and then we play the mapping forward again, and you can see that here's one of the cameras as it proceeds through the system, and then the other camera proceeds in another direction and starts to reactivate previous areas of the map and use that area of the map for both tracking and updating its model. So you'll see as this camera comes around here, for example, it will add extra circles to this region of the map, which shows some of the advantages of this collaborative mapping strategy. At this point, this camera here has finished its trajectory, and this camera continues, but continues in a different direction, adding new regions to the map in this global unified representation. So obviously this is a simulated environment and it's a very simple environment, but it's really just to show the idea and for us to kind of bootstrap our initial research into applying this in outdoor environments. So some obvious constraints here is that we're using simulated data. In terms of our current focus and our future work, we're currently continuing the work with the Urban Canyon dataset and hope to have ATE and reconstruction accuracy results for a future publication. We're also looking at information theoretic approaches that we've previously published and how we integrate those into our dense SLAM system to reduce the computational burden of the collaborative SLAM system, where instead of fusing every single camera into the model at every frame, instead we use information theoretic approaches to identify the frames that have maximal information using something known as the normalized information distance as a mechanism for evaluating the information content. So in order to apply this in outdoor settings and in real-world settings, we're looking at depth prediction networks to generate dense depth of the environment from real-world cameras, and then we're going to input those into the system as we've shown you with the Urban Canyon dataset to evaluate them in real-world camera scenarios. So to conclude then, I presented a collaborative dense visual SLAM system based on an extension of the ElasticFusion system. The system allows multiple cameras with unknown initial transformations to be combined, where loops are detected between the independent submaps, with the submaps being merged into a single unified model, which all cameras share information between. As I said, it permits shared fusion into this single model. I provided quantitative results on 2 benchmark data sets and qualitative results on initial experiments with an autonomous vehicle, simulated autonomous vehicle data set. So I think at that point I'll finish, and I look forward to discussions at the rest of the workshop.